Good morning, everyone. I just have a very quick announcement and I'll get out of the way. Reminder, the second panel is happening today. We have an exciting lineup of panelists. It's going to be at 3:10. If you don't want to remember it, just look at the schedule, 3:10 through 4. We have Misha, Hamed, Russell, Ben, and Leslie in the panel. Please come. It's the same QR code if you want to actually send us questions for the Slido page. That's this one. I'll leave it for 5 seconds if you want to take pictures.
We're not that long around them. Just ask questions.
We'll do that as well. Audience participation is encouraged. And, okay, that's all I gotta say, and then I'll flip over to you.
Okay, so thanks everyone for coming to the morning session. It's a great privilege to have Les Valiant here from Harvard giving the first talk. Les needs no introduction to theoretical computer science. He's been working in this field for a long time, making seminal contributions in complexity theory, learning, parallel computation, and many other areas. He's won many prizes in the field of computer science, most notably the Turing Award. He's a fellow of the Royal Society and the National Academy of Sciences. So let's welcome Les.
Thanks. Hello. Well, thanks for inviting me here. So I'm excited to be here. So I've been interested in this area for a long time, but from the perspective of cognition. And I think the main mystery of cognition is how animals and humans can have a good judgment in very uncertain situations. So it's a question of, so I emphasize making good judgments, getting right answers, and underemphasize other things like, writing email messages in the style of Shakespeare. So that won't be so important for me. So what I'm going to describe is, I have 3 styles of motivation. So if you ask a question, did Aristotle own a coffee-making machine? Then humans, and now also some machine learning systems can answer this. And of course, the point is that neither we nor the machines have seen many examples of the domestic appliances of Greek philosophers. So it's unlikely that we answer this question by straight machine learning, but we can nevertheless do it, and so can some machines. And so the way I interpret this is that what we're doing here is some sort of chaining of uncertain learned knowledge. So when we answer the question, I suppose conventionally we'd say we're doing reasoning. We're chaining together different beliefs we have about when Aristotle lived, when coffee was discovered, etc., etc. And we chain it together, and somehow we manage to get the right answer. So this issue. Sorry?
Sometimes.
Some humans, sometimes. Oh, I don't know. Okay. Yeah, but it's a miracle how we're so good at this. Okay. And somehow this issue has kind of obsessed me for a long time. So maybe so at some point when I got happy about what machine learning was about, I think I decided this was the really important central problem in machine learning, AI, cognition. I've been focusing on this. So understanding why I was so obsessed with this, I only understood more recently, so I'll come to that as well. But so I'll try to say more about this. So the avenue I took, okay, so the question is how do you best solve it? So supposing you want to make the best AI system which can make good decisions like this in an uncertain world, what would you do? And the point is, I think it's unlikely that you would actually build a large language model, because why be obsessed with getting this very good linguistic skills? Maybe you should directly work on this problem. Why be obsessed with predicting the next word? Why would predicting the next word be the avenue to solving this? And I think the answer is that this probably isn't the avenue for solving this. And if you try to solve this problem directly, you do something else. So what I'm going to describe is this something else which I've been working on for a long time. And the advantage of this is that it addresses more directly the issue of giving some principled explanation for why your system is making a good decision about this Aristotle question. Okay, because I think when okay, so basically what I'll describe is based on so by learning I'll mean back learning, and this chaining together I'll basically use a system which I developed a long time ago called robust logic. And if I've got time, I'll try to put this together in a slightly wider context. But just to explain more what I'm talking about, so the way I formulated this question of, what's the principal theory of reasoning in a situation where knowledge is uncertain and learned. So I call this knowledge infusion. That's just repeating a kind of informal definition. So the point is, so you want to store knowledge, but in such a form that principled reasoning on it can be carried out computationally feasibly. So maybe just reading in all the text of the ever written, that may be one way of storing knowledge. But maybe there's a better way. So for example, we humans, we can instantly react to situations and do the right thing. So somehow I believe that in our minds, we do have knowledge compiled so that we're ready to chain together things and do the right thing, recognize elephants, things like that. Okay, and in particular, what one needs to do is to be able to chain together two pieces of knowledge so as to derive a conclusion, and the confidence in the conclusion that is justified can be estimated in a principled way. So this is some principled way of reasoning on uncertain knowledge, and of course using formal logic, these efforts didn't quite pan out, and the reason I attribute to that is that one needs robustness to all kinds of things, and the learning gives you robustness. It tolerates being wrong, but it also gives you robustness, because if your knowledge is wrong, you can learn your way out of it and learn more things. So learning is the solution because it gives you robustness. So in some sense, the old dream of using formal logic for doing this doesn't quite work, because it's not robust enough. But still, you want to do the same. You've got the same task. You want to put in knowledge in such a way that you can reason from it and justify your reasoning. Okay. So just a last slide of a kind of the viewpoint. So I do want to explain how you can chain uncertain learned knowledge in a principled way. And the prime example is the Aristotle and the coffee. LLMs, as we currently understand it, they do some chaining, they do some reasoning, but even when they do, I don't think we understand. It's not very principled. We can't give percentages of accuracy to the predictions. Okay, so the learning part of LLMs, that's very well founded. We know to what percentage it can predict the next syllable, but to actually make predictions about the content, we can't describe probabilities, as far as I know. So in the system I'll describe, you can, and I think it's a good comparison point. And certainly I think a big opportunity in AI is to make systems that operate with broad knowledge more trustworthy. And I think trustworthy, for me here, means that it can be trusted to make good decisions, even when it's combining uncertain knowledge. Okay. Okay, and so I do believe that this is very fundamental to cognition. It's not just some technological next step, simply because for survival, animals do have to make good decisions all the time. And so more recently, I have put this in a broader context, which I may mention at the end. So I've with a broader context of which I describe in this book called The Importance of Being Educable, which basically is a model of cognition. And what I'm describing here is somehow the glue, okay, which I've only recently realized, that you need some central glue to glue together the main parts of it. No, I mean that you can justify, well, maybe you can give a probability of prediction. So if your system that says Aristotle did not have a coffee machine, then that could be principled for various reasons. So one could be that I can persuade you that given its training set on other data, it's a 98% probability that is correct. If there's some, well, it's formal. I mean, one thing is quantifiable. Yeah, I mean quantifiable. Yeah.
When you say the LLM is not principled, it's the opposite. Meaning
Yeah. So I explained that some things about LLMs are quantifiable. So if you want to know with what percentage accuracy the next syllable will be predicted, that's very quantifiable because that's really what it's trained on. And machine learning statistics tells you exactly what, believe, if they said believe the next syllable will be this with probably 78%, that's very reliable. But when it, solves some puzzle for you and chains together some piece of knowledge, now I don't think we can give, sometimes it seems to be lucky sometimes it's wrong. But, I don't think we know when it's right and it's wrong, okay? Okay, so it's as simple as that. So what I'm saying is, in some sense, you can interpret in terms of LLMs, and I suppose the question for, if you really like LLMs, is that maybe you can do something with LLMs and solve this problem. Maybe when LLMs reason, you can somehow calibrate it and say, in this instance, it came to this conclusion, and we can justify it. Okay. So so basically it's when LLMs do some some train of thought prediction or something like that. Yes. Okay. So it's.
it was more than what you meant about us.
Okay. Quantify. Yeah. Quantify. Say quantifiable in this fact formulation. If you can, in a principled way, assign a probability to something, that's what I mean. Okay. Okay. So so I'll just describe this robust logic, and it's okay. So some very basic things which I think are somehow unavoidable. So let's consider that the world is described by Boolean features, like n of them, and they may be vectors. And there are a few things to say. So one thing to emphasize is that the examples from which we learn are very partial. That if you see an example, very few things are specified. And then exactly what this means can become a bit convoluted. But the simplest notion of a feature being unspecified is that it's kind of it's part of the probability distribution. Okay, so the fact that so maybe typically in a situation like this, that I see you but I don't know some facts about you. So these facts about you are hidden, and it's typical in this situation. I shouldn't be surprised. So the simplest notion of undefined is star, which means that it's a three-valued representation, and star means that it's hidden. But it's a distribution over 0, 1, and star. So typical examples come with true, false, or I'm not telling you. So here means unspecified in a natural example. And so this isn't central to what I'm saying, but I'm just mentioning this. So in a very classical AI 1970s and 80s concern, this non-monotonicity was that if a feature E3 says bird, and you're told that in an example, this thing is a bird, and feature E17 tells you whether it's a penguin or not, and you're not told whether it's a penguin, then maybe concluding that this thing does fly is reasonable, because maybe in the real world, if someone tells you it's a bird, and if it were a penguin, they'd bother to tell you. Okay, and so your reason to deduce from the fact that it's you haven't been told that it's a penguin, that it's not a penguin. Okay. So already, I mean, this formalism solves some problems which arise in logic. So this was a problem of non-monotonicity. But okay, but this isn't this is a kind of a detail. But there are other senses in which the world is partially defined, and the second sense is what I call obscured. To use a dollar sign, which is that I give you a natural example, and I obscure one part of it. So this is like if I give you a kind of a hidden word problem, or LLMs do the next word problem. Okay, so the next word exists, but I hide it from you and say, hi, what about it predicted for me? So that's another sense. So there will also be a third sense, which I won't describe, that when you reason in this system, it may be that you haven't given a value to something yet in your reasoning. Okay, so that's part of the complication, which I don't want to go into. But the fact that the world is partially defined is pretty important. So the second feature of robust logic is that it's relational. We take seriously in the sense of predicate calculus and classical AI that the world is composed of several objects and relations on them, and that kind of if you obscure this, which some systems do, then you just lose information, or you may lose information. And so the point is that it may be, okay, so in this system, you wake up, you have a number of what I call tokens, which are kind of not exactly like the LLM tokens, the dark circles, and these are the stand-ins for arbitrary concepts. And you wake up and you think of an elephant, so you ascribe to one token the notion of an elephant. It's a predicate in your vocabulary. And you also got a likes. It's a predicate of two arguments, and you're wondering what your elephant likes. Okay, second object is what your elephant likes. Your elephant likes peanuts. Okay. So in standard logic, there are ways of expressing this. That if there is an object which is an elephant, and there's another object which elephant likes, then it's peanuts. Okay. But in robust logic, we'll try to imitate the same facts. I think we have to put in somehow the same knowledge, but the main difference will be that instead of implications, we'll have equivalences, because in machine learning, you learn both ways. You want to be correct in both ways. So a positive example of okay, so of course for implications, if this is wrong, then it doesn't matter what happens. In machine learning, whichever you want both sides to say about the same thing. So what this will be is that you will have a recognizer, some sort of machine learning system, which will detect peanuts. You'll train to detect peanuts, and the function you've learned will be f. And the learning algorithm you use is whatever you like, but it would better be your favorite learning algorithm, which meets your specifications. Okay, maybe you can afford to train on it. And also, we will assume that for the simplest version, we'll assume that our learning algorithm learns Booleans, in which case we'll have to Booleanize all the description of the world. And we will encode relational fragments as single variables. Okay, so you may want to encode fragments like this, which is a two-variable relation plus a one-variable relation, with the idea that there's one variable which is shared between the two. So then this is really a predicate on the second variable. Okay, so this so this may be part of a definition of peanuts. Okay, that's something which elephants like. Okay, so we're going to learn these. And we're going to learn equivalences. But of course, equivalences we can chain together just like we can chain together implications. So how this will work is that, so I don't have, okay. Okay, so the third question is, what are the examples? And so the domain of examples from which you're learning, you have to define a distribution. So the domain of examples will be a world with a certain number of tokens and all possible relational expressions given your vocabulary up to a certain complexity. So humans supposedly have 7 plus or minus 2 things we can keeping our short-term memory. Actually, it turned out for what we do here, the complexities depend only polynomially on the number of tokens. So apparently that's not so critical. Maybe we have 20. I don't know. It depends how complex scenes you want to describe. But basically, in your mind, all your experiences, you code up like this in your mind. This is your mind's eye, and all the examples you learned are generalizations which hold for things you've seen. It's a very personal view of the world. Okay, and then you learn rules which apply to all the examples you've seen, and you'll use these rules to update these scenes and make predictions. Okay, okay, so the main purpose of all this is to make predictions. You learn rules, and so for example, having the rule I've described, you may make the prediction that this must be peanuts, or it's likely to be peanuts. Okay. Okay, so rules can be applied in succession to train them on an example to which they apply. And this is the method of reasoning in robust logic. So reasoning isn't a formal reasoning system. So reasoning boils down to just chaining together rules which you happen to have. So the view of reasoning here is that so maybe it's now I think it's different from what essentially was word skills were used yesterday. But the idea is that maybe when we learn arithmetic, what it boils down to is that we have some updates. We've been taught some updates about how to do arithmetic, and these are basic reasoning mechanisms for doing arithmetic. And for a different area of knowledge, we have different update mechanisms. But everything is an update mechanism, and for the robust logic, I emphasize that we'll learn these update mechanisms from examples using your favorite learning algorithm, and that's it. Okay. So you can ask various questions, which people are asking more generally, of course, in AI. So this question of, so if I've got a powerful learning mechanism, is reasoning a waste of time? So as other people have asked, maybe if you scale up learning in a bigger and bigger way, we've learned everything, we've got no reason to reason. So here I think one can give some answers for why that's not true. So reasoning has a role. Okay, so I'll come back to the redundancy. What you want to get from the training, if it's to be useful at all, is the notion of soundness, which is a word borrowed from logic, but having a slightly different meaning there. But it'll mean that if you chain together two rules which you believe in, then you should also believe in any conclusions you reach by the chaining. Okay. Okay, so we can describe about reasoning. Okay, so let's just do an example. So this one is, did Charles Darwin own a camera when he was in college? So this is a harder one. Well, I don't know. I don't know how you think about this, but again, there are 1,000 different ways you could reach a conclusion on this, but I just threw down some random ones. So you may think, well, people are mostly in college under the age of 25, and devices rarely exist before they're generally made available commercially. If you look up Wikipedia, it says that the first camera was commercially available in 1839, and he was born in 1809. So maybe not. Maybe he didn't have a camera. Okay.
I don't know if you made it in the middle of the example, so I don't want to cut in.
Okay, no, carry on.
Okay. So there are a number of paths that might contribute to this. For example, if you know that later in life, after college, he made many drawings, he might not have done that if he had a camera. And if he had a camera when he was younger, he might have held on to it or replaced it, because people get attached to useful items and think they deserve to keep having them and so forth. So there are a number of things that might contribute to the conclusion. And so I wonder why your training method is robust logic and not something that can integrate the probabilities in a way that
Well, no, no.
statistician might not
Well, no.
model.
I'm claiming that what I'm going to say applies to whatever you write down.
Yeah.
Okay, this will apply to all the kind of things you've said as well. Okay, so at the end, tell me whether you're satisfied. Okay, okay. So these are random things, and they're all kind of independently reasonable. But I think the main point is that these various things we learn are usually learned kind of independently. So, for example, if you think that people usually in college to the age of 25, you've kind of, don't know what examples you've learned that from. And the devices rarely exist before generally made available. Yeah, so the obscure geniuses who make these things beforehand. But the examples you learn these from usually didn't mix up A and B. Okay, so the main point is that I'm trying to make is that you're combining principles you believe in, which probably you didn't learn with any interference. Okay. Okay, so it may be that there is bad interference, but really it could be bad interference between these two things. There may be people who stay in college for a very long time and they're really geniuses and make their own contraptions. Okay, and in which case chaining these things together may be false. But so with this robust logic, I believe that we learn rules from lots of examples kind of independently and chain them together. And yet, often they're correct. So some of the rules we may believe in to 100%. I think we okay. But so in the robust logic, all that will happen is that if okay, so the probability that it may be that that A or B, if we're chaining A and B together, basically for this argument, they're not foolproof. But if chaining them together gives you a wrong answer, it must be that at least one of them has been used incorrectly. And just by a union bound, if things are independent, then that's all you have to say. Okay.
Some statistical property of random people?
Well, I mean, look, do you believe in statistics or not? I think
apply to outliers.
Well, yeah, I mean, you are using. I think the argument in the back of your mind is, is that there may be lots of other things you know about Darwin, but still, I think I maintain that cognitively, this is what we do. We chain together generalities we've learned, and as long as we're not aware of any bad interaction between this generality and the particular case we've seen, then we apply it. That's my claim. That's my claim is that so in cognition, whenever you have to make a decision, it's a very particular situation. And if it's a life or death situation, you've got a right to be nervous. But I think this is the best we can do. That either we apply either a single rule will tell us this is a tiger, run away, or we have to chain together two rules. Yeah. I mean, this is the conundrum we have to solve. Yeah. So you're right to be a bit nervous. But I think this is exactly the problem. We have to give a rational explanation for how cognition works and how we can make good decisions in a complicated world. So this is So these two questions are perfect. We should be nervous in this, but I think this is the best we can do. That most of our knowledge is learned knowledge from examples. We've learned the knowledge from data, which in a way where we've got no idea how we're going to use the data, but then suddenly someone asks us a question, you have to give me an answer. Okay? Are you happy? So, no. So, are you happy?
Well, there'll be a question period. Yeah, but yeah, I'm generally happy.
Okay, good. Okay, so I think I mean it's a tough problem, but I think this is what we have to somehow explain. That in cognition we're very competent, and we're dealing with information which we have very little understanding of. We haven't memorized all the marginal probabilities. We haven't got all the data, but we can still operate effectively. Okay, so I think.
Like 90 or 95% refer to something real, because, like, for example, like people in college on the age of 25. Well, now it's true. Was it 200 years ago?
Yeah. Okay, so what I'm implying here is that, say, in a computer system, when we learn rules, we should also keep track of how much confidence we have in it and how much it's supported by the data. So this could mean that I've learned this rule, and the data I've learned it from supports it to this percentage. Okay? And again, as humans, I think we keep track of generalities we know about, how confident we are in applying it. Okay, so basically, so the theory is that we've learned these general rules, and also some confidence level of how confident we're in applying it, based on how much support it has from the data we've seen. Okay, so.
So if we have, let's say, 1 billion rules, how are we going to synthesize them to be able to find it?
Yeah. Okay. So that's what I'm coming to next. Yeah. So that's okay. Yes. So it's all a question of complexity. Okay. So one important point is that this gives you something if the world, I say, is modularly learnable. So modularly learnable means that you can learn about when people leave college, you can learn about when devices exist, and you learn these from different small sets of features. And the kind of world is modular in the sense that the interference between these two things is small. It just so happens that ages at which people leave colleges doesn't interfere with the ability to create devices before they were invented. So, okay. So there's this assumption about the world, but in machine learning, there's always the assumption about the world. There's an even more basic assumption is that the world is learnable, right? So in an LLM, you assume that the next word is learnable, maybe a very rare word you won't do very well on. So all this theory makes some requirement on the world, but it so happens that the world is okay. So some things about the world are learnable. We managed to learn some simple things about the world. That's what cognition, I think, is based on. And also, I believe that the world also is. There are many things in the world which are modular. We can learn it in a modular way. And the point in both cases is that if it's this is a belief, but we don't have to be too nervous, because if the world is not learnable, we'll find that out. Okay, so if this thing isn't true at all, then I won't believe it, because the data won't support it to any high percentage. And again, this modular learnability is the same thing, that if you see examples, if there's interference between the two, then maybe you'll see it in examples. If you don't see any interference between examples, and each of these is really accurate, then you can believe in the two. Then the world will show up interference. Okay, so we're assuming something about the world, but we don't have to be too nervous, because if we succeed, we won't succeed in learning if the world is different. Okay, so quick answer to this thing is training redundant, because conclusions can be reached by end-to-end learning alone. So no, I think probably the most important rationale for training is this modularity. Okay, so I think this is why you need training, and no amount of expanding your data for LLMs will help you predict the Aristotle and coffee making machine, in the sense that unless you start generating examples of Greek philosophers with coffee with appliances, So so you can, with modularity, you can solve lots of problems which you got no practical chance of solving by expanding your data set. Okay, so that's the most important one. But also one can make kind of more quantitative cases for. There's some of the things which are widely debated. So if you chain together two rules, how come you haven't learned that combined rule? Okay, maybe you should have learned that combined rule from a big enough data set. And the answer is yes, from a big enough data set, maybe you will have learned the combined rule. But for practical reasons, it just won't happen because the combined rules may be just too many to record. Maybe quadratically more, exponentially more, and you won't be bothered to write down all the rules. And also, they may just become too complex to learn. So it may be that your learning method can learn rules up to some complexity, and if you chain these together, then you get something more complex. And so, in some sense, you could say that standard logic is based on the same idea that in standard logic, reasoning is redundant because everything is a tautology. The logic implies everything. Everything it implies. So why not just write down all the implications of your logic from scratch and do no reasoning? But of course, that's not practical. It's a quantitative notion. So I think it's the same thing happens here, that for quantitative reasons, it's just inefficient to write down all the rules you may have learned. You may be able to learn from, you may be able to get from combining examples. Okay, so the main question is, someone asked, how much principal training can be supported in polynomial time in robust logic? So as I say, for this, use your favorite learning algorithm. An important point is that the features here will be an expanded set of features. And an important notion is that we will use quantifiers. So this was like the elephant one. So one feature will be that X1 has the property that above it there's a roof. Okay, so we may be able to put in compound terms with some quantifiers, and this will be a simple Boolean feature. And looking for this compound feature is something good because it predicts something for us. Okay, so this may predict a house. And the question is how much this explodes the feature set, but there's a lot of issues of how you keep it economical. So you only do the combinations which occur in your data. You only include a small subset of it. Okay. Okay, so this is what you do. So independently quantified expressions means that in these expressions which represent single features, in fact, you can alternate quantifiers as well. You can have there exists for all. So the quantifiers refer to just objects in the scenes, so they don't refer to the world.
Like for a chain, you can do union bound every day. That could be costly if the depth is high. But if the breadth of the tree is high, also you might incur costs because a spurious chain might be taken, any chain might be taken very easily. Don't you have to account for all chains?
Well, I hope I can, but with the union bound, yes.
There are exponentially many possible chains.
Well, it won't be exponential in. I'll show you the quantification. Yeah, I mean that's exactly what you have to worry about. Okay, okay.
I have a different question. So maybe there are like different ways to reason about a particular case. Like in your example, let's say, I don't know, anybody from Darwin family had a camera during college, and then Charles Darwin was a member of that family, so that with 100% certainty gives us that he had a camera. Like, how would you discover like multiple paths and then?
Well, you would follow all the chains, and you may get contradictions. What the proof would say is that if the probability of any applying any rule is small, then to get a contradiction, some rule will be violated. Okay, so you get a contradiction for some rule is just wrong, and that if it will happen with small probability. Yeah, so okay, so simplest incarnation of this, simplest question is, so if I have a rule for predicting elephants, I mean, maybe I have several rules for predicting elephants which are different. Okay, so I'm not sure whether to allow that, but yeah, I'll allow that. But still, if there's some contradiction arises, it must be that some rule is just wrong. Some rule I'm applying is wrong. Okay, I want to show by union bound.
Like both these rules may be correct. It's just basically conditioning on the fact that this was Charles Darwin. He had a camera, but all those other statements may still be correct, and so you may get a like less than 1% wrong.
Well, no, I mean, it's important in this game is that conditioning is that I've only got one base distribution. Okay, so the distribution is everything you can put together in your mind's eye, and everything has a probability. So I think this only works if you've got one distribution, and then the question is, and the rule may be correct with certain probability on the distribution. Does it answer the question? Okay. Okay, so basically the quantitative stuff is that so the main claim is that if you chain these things together, then there's some sort of soundness. You won't make a mistake except with very small probability if all the rules are accurate to high probability. So the only bad parameter is alpha, which is the arity of the predicates. Okay, so if you've got above has got arity 2, there are 2 arguments. So if you allow relations with very, very high arities, then this thing the degree will go up with the arity. So, but no one complains about that. So the idea is we'll divide up the world into in relations with small arities. So in common parlance, there are some relations with high arity. I think famous one from the AI literature is the notion of revenge. So in revenge, there are 4 things. There are two people, 2 acts, etc., with complicated relationships. Okay, so don't have too many relations of high arity like that. And then, so what you want to control is the runtime of your reasoning and the errors. And everything is polynomial in the number of tokens in your mind's eye, and the number of rules, the size of rules. But the maximum arity of relation needs to be kept a constant. So somehow it has to be formulated. So you do a polynomial number of alternatives which you search. Okay. So things are of constant depth. Okay. I mean it's okay. So this all sounds complicated. So a long time ago, with a student Loisos Michael, he implemented this, the natural language system. It was done on the Wall Street Journal database, which was considered large at the time. And the exercise was to compare how well we could predict a missing word using just a naive machine learning system with a naive learning system with this added. And then one found that you could implement this on a laptop at the time using lots of tricks and heuristics. And you got some advantages from doing this as opposed to doing vanilla machine learning. Okay, so this is something which is implementable. Okay, so there are some provisos. So if you, depending on how you interpret what I said, if you make predictions if you update your scene and update your scene again, then you may go into a part of a distribution which is kind of different from what you've learned from. And to treat that rigorously, I mean, that you can do it. We did that in the experiment, but you have to treat each level of update as a different distribution and learn from it. So this paper on this knowledge representation conference. But often the training is kind of really of depth or to depth one, in effect, before you apply some universal rules. So, for example, in the Darwin example, we applied one rule to deduce that Darwin wasn't a student, and another rule to apply to decide that the camera wasn't available before that date, and then we applied something we believed in universally, that this is some sort of law of time, that we can't bridge this. So there are lots of things to say this, but I think my main message is that if you care about justifying the truth of what you're predicting in an AI system, you kind of have to do something like this. Okay. And just a few other comments. So it's not. So again, this work was done before LLMs, although the experiment we did was kind of a language model-like. But just to say some very obvious things. Well, I'm not quite sure to what accuracy LLMs predict the next word. You can find various percentages. But certainly, if you want to make trustworthy predictions in the real world, is this an elephant or not? You want much better accuracy. So where do those much higher accuracies come from? And this robust logic approach gives you a kind of a methodology by which you can try to track down things which are more highly predictable with high probability. Okay, and I would say that's probably psychologically, we humans expect predictions to be, let's say, well calibrated, even if it's out of distribution. So, so if I ask you a question about Aristotle and his coffee making machine, we expect you to, get it right. If you get it right 2/3 of the time, we're not so impressed. Okay. Okay. So. Okay. So, of course, what I'm doing here, I'm giving up on all the beautiful language which LLMs produce. I don't care about that today. But if you care about provable trustworthiness, then there are other ways of going, and this is what I've described. And the main idea is to first to detect relational information explicitly from your data, and then to use it. So some of us who use LLM sometimes think that maybe the LLM, the learning, hasn't even quite picked up all the relational information from the text. It doesn't seem to care that much. So it may not, in the LLMs, it may not. Well, it may be that the reasoning isn't very principled, but it may also be that it doesn't even pick up all the relational information, which I put more emphasis on. Okay. So anyway, so this defines a criterion of trustworthiness, and certainly, of course, people are trying to do this, but I think it's a challenge to do this for LLMs to understand, how much you should follow their predictions each day. Okay, so I'll stop there. Thank you.
Can I view the chaining as a sparse approximation to standard logic?
Standard logic reasoning.
Can I view it in this way?
Well, yeah, in a very loose way, yeah, yes. I don't know, do you have a more technical interpretation? Or?
Yeah, because you mentioned that standard logic reasoning is like too complex for some real-world events. Yeah, so the chain means like you extract some rule in very high level and you put it together. So I view it like in sparsification.
Okay, yeah. I mean, I think there isn't a formal connection, but yeah, okay. That's one way of viewing it, maybe. Okay.
Yeah, this is more of a understanding question, but like, so how does logic relate to robust logic? Like, is logic like a subset of robust logic? Because I would imagine if I have facts that I'm even sure of, and they imply something else, but the proof is very complicated, so it's not very, classical logic, not really polynomial time, right? But as far as I understood, robust logic is polynomial time. So how does that happen?
Well, I mean that this robust logic is okay. So I don't think the two are comparable. Of course, there are many different kinds of logic as well. So it depends which one you compare it with. And so certainly this is a very simple fragment of a logic, which is defined to be polynomial time. So I do just to training, but I do expend quite a bit of time on this relational stuff of matching variables. Okay, so there's this combinatorial part of matching features, but otherwise it's polynomial time. Yeah, so it's defined to be polynomial time, clearly.
So last week there were a lot of talks in this bootcamp for LLMs on benchmark. Like they're trying to, which I don't understand really. Does it meet a benchmark? Does it not meet the benchmark? Maybe we should invent new benchmark. Seems like the wrong way to assess the quality of the system to me. And with your last slide, you're saying you have some criteria. It might be an interesting criteria for trustworthiness, this idea. So I wonder, any thoughts about like what would be what they call benchmark or not a benchmark, but for a test where the system is past the level of trustworthiness? I mean, it's a measure where afterwards you would say, I'm willing to accept it for a certain.
Yeah. Okay, so it's complicated. So in of course in standard machine learning, there are benchmarks which are very important and they were very useful, but that's because the benchmarks, what you test on is really exactly what you define machine learning to succeed on. Okay, so here the difficulty is that you define large language models you train it to do well on the next word, and then you seem to test it on something different. So I presume these benchmarks were like reasoning kind of benchmarks, were they? So people have benchmarks which test kind of.
About quality, about accuracy. It wasn't really. It's just. It's
But
benchmark. Okay, I'm actually more interested in your context. What would be a test? And maybe it's called a benchmark. Maybe it is a benchmark of the sense of a set of it's supposed to succeed on. It doesn't seem like to be the right thing because it succeed on that benchmark. But.
Yeah, I think okay. So when I understand your question, I think there's a difficulty here, which you pointed, is that the LLMs are trained to do one thing, and then you're wondering whether it does something totally different. And then, so supposing you want to do say, well, does a LLM really do reasoning? Then is there some absolute benchmark for testing reasoning? And the problem is that there isn't a absolute absolute definite definition of reasoning. Well, I mean the scientific activity which I'm suggesting here is that so in some sense LLMs. You can relate what LLMs do when they reason to this robust logic, because in some sense, so LLMs do reasoning, for example, in this train of thought thing, where you could interpret this train of thought thing as it's kind of spitting out my kind of tokens. So it's reasoning the tokens it's using in my sense. The only tokens it creates are the ones it actually says. Okay, so it explicitly says my kind of tokens. So you could. Try to assign somehow with what probability these various tokens are true in this sense. So maybe this kind of analysis you could somehow transport to LLMs. I don't quite see how, but it's like a reference point. I mean, using benchmarks, I think, is unless you know exactly what you want to benchmark, what exactly the kind of questions you want your LLM to answer. If it's one kind of puzzle and then next day it's a different kind of puzzle. So the benchmark, you have to somehow define what is where they're drawn from, right? What's the property you're testing.
So, show you through the slide for 1 second.
Okay.
So your takeaway was that you have a criteria of trustworthiness. That's what I was trying to refer to. Can that be applied to any system? It doesn't have to be LLM. It could be other systems. Could that become an effective procedure for the testing whether something is trustworthy or not?
Well, no. I mean, of course, what I'm doing here, I'm using standard machine learning to gauge the trustworthiness of some basic things I learn. And then when I chain these together, I don't want to lose the trustworthiness. I don't want to preserve that trustworthiness. Okay, so I start with trustworthiness, which I understand, basic machine learning, and then I want to hang on to it when I do something more complicated with it. Yeah. So that much I think is a transferable thing. That when you use machine learning in some complicated way, you want to keep track of whether they're still delivering the kind of accuracy which the separate pieces you've learned deliver. So I suppose that's the message.
I just asked ChatGPT that question about Aristotle, and it gives a very reasoned answer. It says, well, coffee was not known at the time, machines in it. Kind of what the human would do, right? So maybe they're already like satisfied. I mean, isn't that what the ones?
Well, yeah. So these very simple standard things that these systems can do well now, they couldn't not so long ago. So not sure why this great improvement, but nevertheless, my experience with large language models is that they don't care that much about ground truth. Okay, that so if I try to find out, asking random questions about something which I know something about, and maybe not very standard stuff, my impression is that they don't care too much about what's true. Okay, so this is for people. So if you're satisfied with current LLMs, so when you wake up in the morning, you don't know what to do that day, you're happy to ask your LLM, what should I do today? If you're confident in the wisdom of its recommendations, then you're fine as you are. Okay, but if you want systems which give you better judgment in this real world, then I'm saying there's something else you can do. Yeah, so I agree that these large language models do quite well on some of these things. And of course, people research how it's done. So this chain of thought method is effective, and that's we can understand in these terms that you just. But I'm saying that if you care what I care about, you can try to do it directly, and maybe you can do better on this than using large language models, which are very good at something else, but maybe they're not optimal at this. So I think it's a alternative possibility, and trying to do everything through large language models. I see the traction because it spits out this very nice language. I see why it's hard to resist, but it may not be the best for everything.
You want to type stuff in?
Sorry?
Just type stuff in and it gives you answers.
Yeah, the natural languages is great. Yes, I agree. Yeah, sorry.
I think that what's very powerful maybe in LLMs is that a priori, for like a very complex situation, the world in its totality, we don't know what are the variables. We don't know what are these x's. We don't know what are the relations. And somehow, it's a very messy system with a lot of parameters, whatever, but like it manages to extract automatically features and things that like otherwise we don't know how to define for Darwin and coffee, but for a million things you don't know. And I think there are some approaches now that maybe allow us to open a bit black box like this sparse autoencoders and things that allow you to somehow read off some of those features and maybe try to understand what happens with them. Like there was a sparse circuits and I don't know. There are some tools that people are trying to introduce, but my question is, how do you see a combination of both of these worlds? Like, how can we still retain some of this automatic or automatized feature extraction and relation extraction? And how do we reincorporate there some notion of like trustworthiness or like probabilities, or where are the probabilities in that procedure, or like how do you see like a reconciliation of this?
Right. Yeah. Well, just the first point is that for this robust logic, implementing it isn't that much more complicated. Well, complicated. It may be more time-consuming, but I mean, basically, we assign tokens to words, say more common words, but we also put in the facts about how this word has got two arguments. So we put in some sort of linguistic things, but they weren't difficult things you could find in a dictionary. So applying this to natural language isn't hard. That's what we did. But except we worked on a rather small data set which was available. Yeah, on your second question, yeah, so I don't see clearly how you can integrate the two things just like that. But the people who think about LLMs, I think a simple challenge is to, I think, assign probabilities to the predictions in some way similar to this, I think. So I think that's a reasonable expectation that if you believe in LLMs and you think it'll give you wise judgments, you should be able to justify it. The fact that you can't justify it may mean that it's really unwise what it says. Okay, so if you just use a tool and you've got absolutely no understanding of why it works when it works, sometimes it doesn't work. That may be dangerous. Okay, so I think so. The way I phrase the title, what I'm saying is that this kind of criterion may be useful in thinking about LLMs. I mean, you're asking the real question of how you can get the benefits of both in a single system. And I don't know.
Okay, so I share your